Okay, so to extend the concept of exponential functions, we are going to now talk about exponential growth and exponential decay. First, I'm going to talk about exponential growth. And exponential growth is an exponential function in this form, y equals a times b to the x power, where a is greater than 0, meaning a can't be 0, a can't be negative, and b has to be greater than 1, which means b cannot be 1, and b can't be less than 1 for this to be exponential growth. The base b we call the growth factor. That tells us how fast, how quickly the function is growing. The coefficient a, the number multiplied on the front, is the initial amount. I call it usually the starting value. So this little diagram kind of gives us a good visual of what the parts of this exponential function are. So to model exponential growth, in example 1, it says, since 2005, the amount of money spent at restaurants in the United States has increased at about 7% each year. In 2005, about $360 billion was spent at restaurants. So if the trend continues, about how much will be spent in 2015 using that trend. So in this function, we're going to use that y equals a times b to the x, and it's understanding that in this function, a, the starting value, is 360. Now the growth factor is not 7. To represent a growth of 7%, we're going to represent 7% growth as a decimal. So to represent 7% growth, I would do 100% plus 7%, which equals 107%. But I'm going to convert that percent to a decimal. 107% as a decimal is 1.07. So that is my growth factor. So I'm going to write the function first. Y equals the starting value, 360, times 1.07 to the x power. Now in this function, I'm asking you to find out how much was spent in 2015. So I've got to know what to substitute in to x to find what was spent in 2015. So this function represents years since 2005. So 2015 is 10 years after 2005, so I would substitute 10 into this function. 360 times 1.07 to the 10th power. So I would like you guys to take a minute to do that in your calculator. That's 1.07 to the 10th power, and then multiply that in the end by 360. We get about $708 billion spent at restaurants. So that trend is growing. More people are eating at restaurants. So in part B, the expression that represents the monthly increase of spending, so the monthly increase is basically saying that we would take 1 plus, now to represent if we increase by 7% each year, we would divide that 7% increase over 12 months, okay, if it was monthly. So we divide that 7% growth equally over 12 months, and we would add that to 1 in our calculation. And that's kind of a nice segue, a nice connection into the next type of function we're going to talk about. It's an exponential growth function, and it has to deal with something called compound interest. So when you have an account in a bank, that account pays interest on both the principal, the beginning amount in that account, and the interest that that account accumulates. So the bank pays compound interest in that situation. Compound interest is exponential growth. So we're going to get some vocabulary words down right now. The principal is the starting value, okay? In this function, it looks complex at first, but it's really not once we do a few examples. R is the interest rate as a decimal. N is the number of times the interest gets compounded in a year. So if I say, if it gets compounded monthly, I'll do quarterly. 4 times in a year. N would be 4. Quarterly. If it was monthly, this would be 12. This would be 52 if it were weekly. N would be 365 if this were being compounded daily. So that's what n means, the number of compounding periods in a year. And t is always in years. Every time t is in years. So to go over an example of this, compound interest says suppose that when your friend was born, your friend's parents deposited $2,000 in an account that pays 4.5% interest, compounded quarterly. What will be the account balance after 18 years? So I'm going to write out all of the variables that we need in order to evaluate this. So in this function, this compound interest problem, the initial amount, the principal, is $2,000. The interest rate as a decimal, this percent as a decimal is 0.045. It's compounded quarterly, so that means 4 compounding periods in a year, and we're putting it in the account for 18 years. So the time t is 18. So the amount, and this part we're going to get used to, you're going to get practice on this. The amount after 18 years is going to be 2,000 times 1 plus the interest rate as a decimal, 0.05, divided by 4 times a year, and that's going to be raised to the number of times it gets compounded in total. So if this is getting compounded 4 times a year for 18 years, it's going to get compounded 4 times 18 times, which is 72 times. So I'm not going to show this on the screen, but I'm going to talk you through how to plug this into a calculator. So I'm going to use ordered operations, which means I'm going to do the parentheses first. Inside that parentheses, I'm going to do the division first. So I would do 0.045 divided by 4, hit equals on my calculator. Take that number, add 1 to it. That completes the parentheses. So the next step is to use the exponent. So that number I just got in my calculator, I'm going to raise it to the 72nd power. I'm going to leave that in my calculator to get as precise of an answer as I can. Take that number, multiply it by 2,000. So the amount in this account after 18 years, $4,475.53. That is the amount in the account. So we will get practice on this eventually, and you're going to know how to calculate compound interest, because I think that's an important thing to understand how compound interest works. So that's our last example of exponential growth. I'm just going to finish it out by talking about exponential decay. So with exponential decay, everything is the same. The one thing that changes is that the growth factor now, instead of being greater than 1, the growth factor is going to be between 0 and 1, because the amount is decreasing. So the way you decrease something using multiplication is by multiplying by a number that is between 0 and 1. That number, I shouldn't cross that out, that number is called the decay factor. I'm going to show you that in example 3. And this is a really common example. When you buy a car, it loses value. When a car loses value, we call that depreciation. So in this exponential function, the starting value of this car is $20,000. Okay? The car decreases in value by 20% per year. So the way I'd figure out the decay factor, if it's decreasing in value, I'm going to subtract that value from 100. So that means 80% of the value of the car is left after each year. That percent as a decimal is 0.8. So my function is y equals the starting value, 20,000, times 0.8 to the x power. And it's asking the question, after 6 years, should they sell the car for this much money? So let's find out the actual value of this car if it depreciates at this rate after 6 years. So that's essentially me just substituting in 6 for x. So I would do 0.8 to the 6th power, figure out what that is, and then multiply it by 20,000. So after 6 years, this car would be worth $5,242.88. So the answer to this question would be no. The car is worth about $1,200 more. So you could sell it for more than that amount because the car is worth more, obviously. So you can sell it for a higher amount. So in the guided practice, I'm just going to go through these just to show you, just to give you more examples, and then you can get some practice on your own after this. So in number one in this guided practice, it says, suppose the account in problem 2 pays interest compounded monthly. What will the account balance be after 18 years? So I'm going to give you back the information. This account started with a principal of $2,000, had an interest rate of 0.045 as a decimal. Now, this problem, instead of compounding quarterly every 4 times a year, this would be compounded monthly 12 times a year. And then it's still 18 years. So all we're changing is the number of times it compounds. So my function, or my expression that I'm going to write, same thing, 2,000 times 1 plus 0.045 divided equally amongst 12 months in a year. And if it's compounded 12 times a year for 18 years, that's going to be raised to the 12 times 18 power. So 12 times 18 is 216. So kind of a big number. So again, order of operations. Inside the parentheses, divide 0.045 by 12. Now, add it to 1. Get that number equaled out. Raise that to the 216th power. And then finally multiply it by 2,000. So sorry, that's not the principal. I shouldn't have written that. This is the amount, after all this time. So the amount in the account is $4,489.01. So if I keep everything else the same, but I compound the interest more frequently, I would end up making a little bit more money. So in the end, the last guided practice is actually a little bit easier to set up. You need a starting value, you need a decay factor. So the starting value in this function, it says the population of the city starts at 45,000, and people are leaving. They're losing population at 2% per year. So in this function, I don't know why I capitalized A. I'm just going to do a lowercase a here, lowercase b. If they're losing 2 people a year, or 2% a year, I would get rid of 0.02 as a decimal. So that means 98% of the population is still there. So to figure out how many people are left after 15 years at this decay rate, I start with 45,000 times 0.98 to the 15th power. Okay, so 0.98 to the 15th power first, hit equals in your calculator, then multiply that by 45,000. So this is how many people would be left after 15 years. 33,200, and I would say 236 people, because it's like 35.6. So I'd round that up. So that would be the population. And I think that's kind of significant because when you're predicting a population, that can decrease. I mean, it's a lot of people. 12,000 people is a lot to lose in a city. So now you're probably ready for some practice on writing the functions, evaluating the functions, so you can move on to the next step of the lesson.